So in this video we're going to look at three things. We're going to work towards finding the inverse of a matrix, and to do that we need to understand what an identity matrix is and what the determinant of a matrix is. So first of all we're going to go over the identity and the determinant, and then we'll lead into finding the inverse of a matrix. So we're only looking at 2 by 2 matrices, I should say, for finding the inverse. It gets very complicated doing a 3 by 3 or something like that. It's something that you might study in university, and it'll be quite complicated. Things kind of have to overlap a bit and multiply by new things, and it gets very confusing. We're only doing 2 by 2s, but again, much quicker to do in your calculator. So always use your calculator if possible. So let's look at identity matrices. So I is the letter we use to represent an identity matrix. So if you set this letter I somewhere equals I, let's reserve that letter for the identity matrix. Don't make a normal matrix the letter I. Even if your name is Inga and you want to use the letter I, just save it Inga. Let's just go with A instead. So I is the identity matrix. It works like the number 1 when you're multiplying, at least. If you multiply by the matrix I, the identity matrix, the answer will be the same as the original, just like 10 times 1 is still 10. Kind of works that way. So here's some examples. If you have a matrix A and you multiply by I, the answer is going to be A, like just the same, nothing changed. If you get the matrix A and you times it by 1, then it will just be A. So the same thing. Or if you want to do, flip it around, different multiplication, I times A, that'll equal A. 1 times A, that'll still equal A. Or if you want to do the identity matrix times the identity matrix, like 1 times 1 effectively, that's just going to come out with an identity matrix, or 1 effectively. So just like if you multiply the identity matrix by 1, it's just going to come out as the identity matrix. So at least when we're multiplying by the identity, it's effectively the same as multiplying by 1. And because it pretty much is a 1, only it's a matrix form, so you'll see some zeros and ones in it. But trust me, it works just like the number 1. So to get an identity matrix, we need to multiply a matrix, not an matrix, good one, by its inverse. So for instance, if we're going to start with A and we want to get the identity, we have to multiply it by its inverse. So that little -1 means the inverse of A. So A times the inverse of A is 1. And we're going to look more about inverses later and how that works. Same thing, if you multiply B by its B's inverse, that'll form an identity matrix as well. And the size will depend on what matrix you're multiplying by what matrix, but nonetheless it will be some sort of square matrix as an identity matrix, and I'll kind of give you some examples of what they look like just in a minute. In fact, let me double check that I did. Nope, I didn't. Let me draw an identity matrix for you. So here's an example of an identity matrix. This is a 2 by 2 identity matrix. So what we'll see is the 1s go diagonally and the rest of the things are 0. Let me do another one. Let me do a 3 by 3 identity matrix for us. So 1, 1, 1, and the rest are just going to be zeros. There you go. There's a 3 by 3 identity matrix. So it's a bit complicated to understand why that kind of makes it equal 1 when you multiply it. But if you did it manually, you'd kind of see why it works. You just have to trust me that if you multiply this identity by any matrix with any numbers in it, it'll just be like the original. It won't change the original. Maybe you'd like to try that just to sort of have a bit of fun, if you find maths as enjoyably fun as I do, and you could see that that works. But I promise you, it does work. These are some identity matrices. You could do a 4 by 4, and that would have 1s all the way down to here, and then the rest would be zeros. A 5 by 5, a 6 by 6, all the way up to infinity, but the 1s would go diagonally and the rest of the things, the rest of the elements would be 0. Alright, let's move on to the determinant of a matrix. Here's some notation of what it kind of looks like. If you see det bracket A, that's the determinant of matrix A. Very occasionally they do it with these straight brackets here. That also means the determinant. Very rarely would you see that in further maths. You might see it in some alternative textbooks, or if you're looking online for something to do with determinant, it might show you. But generally they write it det A, determinant of A. So, for instance, if we label all the elements in this matrix A, B, C, and D, to find the determinant, we have to multiply these two, A times D, and then subtract the multiplication of these two, B times C. So AD minus B times C. I might just do that in purple for us. A times D minus B B times C. And you would have seen that in that video that I sent you, and he called them the primary and the secondary or something like that. I've never heard what he's talking about. Nonetheless, A times D minus B times C. So it's not, later on we'll get to inverses and you'll see this all the time. The determinant is not 1 over AD minus BC. The determinant is just this bit down the bottom. Just A times D minus B times C. I'll put it in a box for you so you don't forget. If there's anything that you'll forget and lose a simple mark for, it's saying that the determinant is that, which it is definitely not. It's just this bit, AD minus BC. That's an easy thing to kind of forget as we go on, because we start seeing this all the time, and it kind of can distract us, and we can kind of get used to that being the determinant. It's not the determinant. This is the determinant here. So let me give you an example. We're going to find a determinant of this matrix B, so the det of B, 2, 4, 2, and 3. I'm going to do A times D, that's 2 times 3, minus B times C, that's B times C there. AD minus BC, so 2 times 3 minus 4 times 2. So 2 times 3 is 6, 4 times 2 is 8. I'm going to do 6 minus 8, which is negative 2. That's fine that it's a negative number, but we don't see them much, but that's absolutely fine. The determinant of this matrix B is negative 2. Let me see if I gave you another example. Nope, I didn't. If you want some more examples, just come and see me, and I'll show you how to find the determinant of some different matrices. But we only really manually find the determinant of a 2 by 2 matrix. Even so, I reckon if you had this, it'd be quicker just to write det bracket B bracket in your calculator, and it would tell you what the determinant was. It would tell you negative 2. So pretty much everything we do in matrices, you can do in your calculator, and it's not expected that you'll be able to do it by hand, because you'll always have your calculator with you. And last but not least, I know I'm dragging on now, but let's look at the inverse of a 2 by 2 matrix. So the inverse of A, that's that A to the power of negative 1 that you've seen before. You could easily write in your calculator A to the power of negative 1, and it will do the inverse for you, just like that. But I'm going to show you how to do it manually, just in case you're interested. So let's have the same matrix again, A, B, C, D. Then the inverse is 1 over the determinant. Remember, the determinant's just the bottom bit. 1 over the determinant times, I've switched A and D here. You can see A and D have switched around. And then these two became negatives. So negative B, negative C, then A and D is flipped. That's what the inverse will look like. It's flipped these bits and then put a determinant at the front. Another way to write that is 1 on AD minus BC. Like that's the determinant down there, and this is the same. So let's do that together. Here's R, 2, 3, 4, 10, and here's my inverse. I'm going to find the inverse of R. So first I'll find my determinant of R. So the determinant of R, you remember, AD minus BC, 2 times 10 minus 3 times 4. So 20 minus 12, which was 8. So the determinant for this R matrix was 8. The determinant of R equaled 8. So to find the inverse, we're going to have to do 1 on the determinant, or 1 on 8, and then switch those inside bits. So D and A, that was 2 and 10, we switched them and it became 10 and 2. And 3 and 4, we put them as negatives, and that was negative 3 and negative 4. Again, I'll say it one more time, you don't have to do it manually. It's much more time consuming to do it manually. I would always do it with my calculator in an exam or a SAC, or even your workbook to get practiced. I would always do it on your calculator. The calculator can do it for you very, very, very quickly. So if you prefer, you could multiply this 1 on 8 into the matrix. That's that scalar multiplication we talked about. This is 100% marks, that's fine, but if you want to multiply it in and take the risk, you can. Your calculator will do it automatically for you. So you could, if you preferred, write it like this: 10 divided by 8, negative 4 divided by 8, negative 3 on 8, and 2 on 8. Like I just divided it all by 8. And again, if you want to simplify it, you can simplify it. Or if you just really love decimals, you could change all those fractions to decimals. The calculator will by default do it as decimals for you, rather than this nice little neat version that we get when we do it by hand, 1 on 8 and this bit here. It doesn't matter, everything will give you 100% marks, either of those 4 different things I just showed you there, 1, 2, 3 or 4, they'll all get you 100% marks. It's just up to you which one you find easier. Your calculator will do this one for you, whichever, it's up to you. And that's inverses.